welcome everyone this week to our core volunteer training. It is our Ask Me Anything with this quarter's focus, Dr. Ben Santer. Dr. Ben Santer, research scientist and visiting scholar at the Woods Hole Oceanographic Institute, is going to join us tonight. Dana is going to give us an introduction in just a little bit to present his groundbreaking climate science research and field your questions about climate change science, especially with the recent heat waves that we're seeing across the world and any of the other extreme weather events that you're noticing. If you are interested in asking the climate scientific connection, Dr. Santer is your man tonight. We also have a wonderful link to his most recent paper that he'll be debuting here. You can see on the slide. That's available in the chat for the lay audience, a 7-page PDF summary of Human Fingerprints in the Sky. We'll drop that a couple of times. But without further ado, I'll pass it to you, Dana, and we'll get this party started.
All right, thanks, Brett. Hey, everybody. So we are very fortunate tonight to have Dr. Ben Santer. He is an atmospheric scientist and visiting scholar at the Woods Hole Oceanographic Institute. His research focuses on such topics as climate model evaluation, the use of statistical methods in climate science, and identification of natural and anthropogenic fingerprints in observed climate records. Dr. Santer's early research on the climatic effects of combined changes in greenhouse gases and sulfate aerosols contributed to the historic discernible human influence conclusion of the 1995 IPCC report, and he served as convening lead author of the climate change detection and attribution chapter of that report. And he's won a whole bunch of awards and is generally a climate science legend, and so we're very happy to have him. And Ben, you can go ahead and have the floor and talk about some of your recent research.
Thank you very much, Dana. Thank you, Brett. And it's wonderful to talk about this new paper. I'm excited about it. It came out back in May in Proceedings of the National Academy of Sciences. And for me, this has been a 30-year odyssey. So I'm going to tell you a little bit about that odyssey today. Here's the structure. First of all, I'm going to give you a little introduction to what we're going to be talking about, layers of the atmosphere. Then I'll talk about some of the history. What is fingerprinting and why did we decide to do this work today? Who are some of the folks who actually motivated this work? What are their stories? I'm going to spend most of my time talking about what we actually did and looked at, the vertical structure of temperature changes from the surface of the Earth right up to about 50 kilometers, 31 miles above the Earth's surface. And I'm going to break that down into two parts. One part is global mean temperature changes. I'm going to show you time series of how the stratosphere temperature and troposphere temperature have actually changed over the last 37 years. And then we're going to look at patterns, fingerprints, and see how they enable us to separate human and natural effects on climate. And finally, some conclusions. All right, so a brief primer to the layers of the atmosphere, 5 main layers of the atmosphere. We're going to focus today on 2, on the troposphere, the lowest layer of Earth's atmosphere, extending from the surface to about 20 kilometers above the surface, 11, 12 miles or so, and the stratosphere, again, which extends from the top of the troposphere to about 31 miles, 50 kilometers above the surface. Now, we have these amazing measurements from polar orbiting satellites of atmospheric temperature. How does that work? Microwaves are emitted by Earth's atmosphere, and those microwaves are measured by polar orbiting satellites that carry these so-called microwave sounding units or advanced microwave sounding units. And higher temperatures mean more microwave emissions from oxygen molecules. And by measuring at different microwave frequencies, you can literally back out the temperature of different layers of the atmosphere. That's what we're going to be focusing on today, these microwave sounding measurements of atmospheric temperature of different thick layers of the Earth's atmosphere. So these are essentially, this is pretty complicated. Let me just briefly explain. These are different channels, different measurements from these microwave sounders. This in yellow, for example, is the so-called temperature of the lower stratosphere. And most of the emissions that these microwave sounders are sampling for this particular channel peak at about 18 kilometers above the Earth's surface. Here you see tropospheric. This is the temperature of the mid-troposphere down here. And the kicker is that until relatively recently, the kind of work that I do and my colleagues do in fingerprinting had been confined to below 20 kilometers. We were looking at satellite data that measured this part of the atmosphere from the surface close to 25 kilometers. But now in this study, we're going way above that. We're going from 25 kilometers to about 50 kilometers using temperature measurements from the so-called stratospheric sounding unit, channels 1, 2, and 3, and that enables us to probe a layer of the atmosphere that we haven't really probed in fingerprint studies before. We're going to look at 6 different layers in this talk. The 2 here in orange and red are in the troposphere, the lowest layer of the atmosphere. So the layer of the atmosphere that has warmed over the period we've been making these satellite measurements of temperature. And then we're going to be looking at 4 layers above that, the lower stratosphere and these 3 channels above 25 kilometers that look at the mid to upper stratosphere. Like I said, all the pattern-based fingerprint work that had been done previously before this new paper really focused on these 3 layers here, the lower troposphere, the middle troposphere, and the lower stratosphere. What we did in this recent paper is we went above the lower stratosphere and really looked at this mid to upper stratosphere as well. Some history. So this gentleman is very famous in our field, Suki Manabe, formerly from the Geophysical Fluid Dynamics Lab in Princeton, was one of the 3 recipients, co-recipients of the 2021 Nobel Prize in Physics. And his citation had this quote here. He was awarded 1/3 of the share of the Nobel Physics Prize for physical modeling of Earth's climate, quantifying variability, and reliably predicting global warming. So one of the things that the Nobel Committee highlighted was this paper that Manabe and a colleague of his published in 1967 in the Journal of Atmospheric Sciences. So well over 50 years ago. What did they find? They used a very simple climate model, so-called radiative convective model, that only looked at global mean temperature changes in response to CO2 increases, but it looked at those changes from the surface right up to 45 kilometers above the Earth's surface. And what Manabe and Weatherald found in this simple model was when they increased CO2 levels from 150 to 300 to 600 parts per million, the stratosphere cooled and the troposphere warmed. This is 1967. We don't have the satellite data to determine whether, in fact, the stratosphere was actually cooling. We do have some weather balloon data, but most weather balloons available back then in the 50s and 60s didn't have the structural integrity to get well above 20 kilometers. They burst in the thinner atmosphere when they got about above 25 kilometers. So this was a true prediction. Manabe and Weatherall predicted we continue to burn fossil fuels, increase levels of CO2. This is what we should see. And the test of any theory is how good is it, and can what they predicted be verified with actual data? We'll look at that shortly. So one of the questions is, why does increased CO2 cool the stratosphere? And that's a little complex, but I think it's worth showing you this figure here. So this is the downward radiation from the sun. Most of it's in visible wavelengths here. So this is wavelength here along the x-axis. And here's the ultraviolet, visible. Most of the radiation that we receive from the sun is in the visible. And this is the outgoing radiation as the sun heats the Earth's surface and atmosphere. This is the radiation that the Earth is trying to shed to space. And the kicker is that the Earth is trying to shed heat to space in the infrared, where there is a window in water vapor, where water vapor is not absorbing very much of that heat, but where carbon dioxide is filling some of that window. And that's why carbon dioxide is so important as a greenhouse gas, because it's absorbing some of the heat that would otherwise escape to space through this window in the water vapor absorption spectrum. So the key point here is that the largest absorption band of carbon dioxide is not far from this thermal maximum that the Earth is trying to shed heat to space in. And therefore, it's partly closing this window here. So more fossil fuel burning, more CO2 in the atmosphere, more effective trapping of heat lower in the atmosphere. And one of the consequences of that is that the stratosphere cools, as Manabe and Weatherald predicted. And another thing you can see here is the cooling, it is predicted to become larger the higher up you get into the stratosphere. So were they right? Well, in order to look at whether Manabe and Weatherald were right, enter this gentleman here, Klaus Hasselmann, who also in 2021 won another third of the share of the Nobel Prize in Physics. He looks a little like Kenny Rogers. And in fact, when I was on a flight from Frankfurt to Denver many years ago, he was actually mistaken for Kenny Rogers, and we got bumped up to business class, which was kind of cool. Hasselmann's citation from the Nobel Committee was for developing methods for identifying specific signals, fingerprints, that both natural phenomena and human activities imprint in the climate. So basically, Hasselmann's insight was look at patterns. If you want to try and disentangle natural effects on climate from human effects on climate, don't just look at global mean temperatures, look at complex patterns. And this is an example of that. This is looking from the North Pole to the South Pole and from the surface right up to 30 kilometers. And these are simulations that were performed a long time ago now by colleagues at the National Center for Atmospheric Research in Boulder, where using a general circulation model, they changed just one thing at a time. They changed the sun's energy output according to our best understanding of how the sun's energy may actually have varied over the 20th century. And in their model, this was the fingerprint of a slight uptick in the sun's energy output, heating throughout virtually the full vertical extent of the atmosphere. They did the same thing with changes in volcanoes. Again, given our best estimates of historical changes in volcanic activity, they put that in this model, and this is the vertical fingerprint they got. Again, from the North Pole to the South Pole, surface up to 30 kilometers. This was their fingerprint of greenhouse gas changes, human-caused changes in greenhouse gases, with cooling of the stratosphere, warming of the troposphere. This was their estimated fingerprint of sulfate pollution. And this was their estimated fingerprint of human-caused ozone depletion. I'm not going to get into the details, but you get Hasselmann's point from this. They're different. Each of these 5 patterns is different. And Hasselmann's insight was we can use this pattern information to disentangle natural effects like natural changes in the sun and volcanoes from human effects. And basically that was my job when I went to the Max Planck Institute for Meteorology in 1987 to do my postdoc with Klaus Hasselmann. I had the extraordinary privilege of trying to implement some of his fingerprinting ideas in the real world. All right, well, let's now look at observations and model simulations of the vertical structure of atmospheric temperature change. I'm going to show you these first, not in terms of patterns, but just in terms of global mean changes. So the average change in one of these 6 layers that we were talking about. Again, these are the 3 layers that people had been looking at traditionally, that we had been looking at in fingerprinting: the lower troposphere, the mid-troposphere, and the lower stratosphere. I'm showing you these things from 1986 through to 2022, so 37 years of data. The 1986 start is because the next panels I'll show you for the mid to upper stratosphere, we only have a continuous record from 1986 onwards. What you can see here is the lower troposphere has warmed, the mid-troposphere has warmed, and the lower stratosphere has cooled. This spike here is the effect of the eruption of Mount Pinatubo in the Philippines. When you have a big volcanic eruption like Pinatubo in June 1991, some of the sulfur dioxide that the volcano pumps into the lower stratosphere forms liquid phase sulfuric acid droplets. Those droplets absorb some of the incoming sunlight and some of the outgoing heat from the Earth, warming the stratosphere and cooling the troposphere. I should explain here that the blue lines are the satellite observations, and the gray lines are from the latest, greatest model simulations from 9 different climate models that participated in phase 6 of the so-called coupled model intercomparison program. These were simulations that fed into the most recent report of the IPCC. So now we're adding these 3 new layers here, going up to the upper stratosphere here. And what you can immediately see is the stratosphere in global mean terms has cooled substantially above 30 kilometers. Look at the global mean changes here over this 37-year period. They're huge. In this upper layer here, it's over 2 degrees Celsius cooling. Now, if you look carefully, you can see that in both the model simulations and the blue line, the satellite data, there's this roughly 11-year solar cycle. This is solar maximum, this is solar minimum here. The kicker is that the solar changes and the year-to-year internal variability, natural variability of the climate system is very small up here in the stratosphere compared to the size of this huge cooling trend. Again, a trend that was predicted by Manabe and Weatherall way back in 1967. So it suggests even without doing any complex pattern-based fingerprint analysis, this is a favorable region of the atmosphere to look for a human-caused cooling signal, because the cooling is very large and the noise associated with changes in the sun or natural internal variability is very small. A couple of other interesting points to make here. So this, vertical line, this is still the effect of the Pinatubo eruption in 1991, but also have a look at this little blip here. These are the catastrophic Australian wildfires from 2020, the so-called New Year's fires. They were powerful enough to loft soot into the lower stratosphere, where it heated the lower stratosphere and actually cooled the troposphere. You can see that nicely here. So with more potent wildfires, one of the concerns is we're actually changing the chemistry of the stratosphere and mimicking the effect of volcanic eruptions, which I think is a relatively recent understanding. And if that continues going forward with more intense wildfires, then that human-caused changes in the chemistry of the lower stratosphere, which, for example, Susan Solomon and colleagues have studied at MIT, is something we need to be aware of. This just looks at the previous figure in terms of trend space. So these are global mean trends over 1986 through to 2022. And I'm going to build this figure up. What you see here, first of all, are the model results from these latest, greatest model simulations. The black is the average of these 9 different models. The gray dots are the individual model simulations. You can see this, if you're on the right side of this red line, the stratosphere has cooled. And again, this cooling can be very large in the uppermost layer here, 45 kilometers above the surface. And in the model simulations, the troposphere warms. These are simulations that are so-called historical runs that have our best estimates of the changes in greenhouse gases, sulfate pollution, ozone, land use changes. So these are our best shot, if you will, at running models with estimates of the factors that actually changed in the real world. Now I'm going to add so-called world without us simulations. These are simulations from the same 9 models, many thousands of years, but these are world without us runs. So they have no year-to-year human-caused changes in greenhouse gases. And because we have thousands of years, we have many samples of 37-year natural trends in stratospheric temperature or in tropospheric temperature. And the kicker is that natural changes in the stratosphere are very small. So if you look at this distribution, its values range from about minus 0.3 degrees Celsius to plus 0.3 degrees Celsius. So by chance, natural fluctuations in climate can give you small net positive or net negative trends, but they're nowhere near the trends you actually get when you run the model with human-caused changes in greenhouse gases. Well, why is that? It's part because the stratosphere is dry. There isn't a lot of weather up there. So again, this is a favorable place to look for a human-caused perturbation in temperature relative to the small intrinsic climate variability up there. And you could see that also here. Look, the blue is the satellite data. Look how small these variations are relative to the 2 degrees Celsius global mean cooling trend. It's a good place to look for a human-caused cooling signal. And just finally here, I'm adding in colors here the satellite data. Here in the uppermost layers, we only have satellite data from one group. In the lower stratosphere and in the troposphere, we have results from multiple groups, which is why you see multiple colored dots there. The kicker is, again, that in both the troposphere and in the stratosphere, internal variability can't explain the warming we've observed or the model predicted warming that should have occurred in these world with us simulations. All right, so what do the patterns look like? Moving from global mean space to patterns of change, we're looking at 9 different climate models here, 4 in this row, 4 in this row, 1 here. This is the average of these 9 models. These are temperature changes over this 37-year period for which we actually have satellite data. from the South Pole to the North Pole, and from the surface up to 50 kilometers. And in every one of these 9 models, and in the average of all the models, the lower atmosphere, the troposphere, warms and the stratosphere cools when you increase greenhouse gases. If you look at 2 different satellite data products, they show a similar story, similar patterns, warming of the troposphere, coherent across latitudes, cooling of the stratosphere, and most of the warming is, or the largest warming is over the Arctic, where Arctic sea ice has decreased by about 50% since the beginning of satellite measurements in the late 1970s. So these are the patterns we're going to deal with now. And I just want to give you some brief flavor without getting into equations of what fingerprinting actually does. What does it involve? So imagine you have these satellite temperature measurements from the South Pole to the North Pole along the x-axis here, and from the surface up to 50 kilometers. And we're going to step through the satellite data 3 years at a time, 86, 89, 92, 95. And over time, you can see what you could see in global mean space. The stratosphere has cooled and the troposphere has warmed. Now we want to compare the sequence of patterns with the model predicted human influence fingerprint. This pattern in response to greenhouse gas increases of warming of the lower atmosphere and cooling of the stratosphere. And when you do that, when you calculate some measure of pattern similarity between the satellite patterns and the model predicted human influence fingerprint, you get this time series here, and it shows a trend. It shows what you can see with your eyes. The satellite data are over time becoming increasingly similar to this pattern. Now it has some wiggles. This little dip here is the cooling caused by Pinatubo that I mentioned earlier, which yields warming of the upper atmosphere and cooling of the troposphere. So one of the questions is, can natural causes generate some pattern similarity just by chance that rivals or exceeds this trend that we get when we compare the actual satellite data with a fingerprint? So we need what statisticians call a null distribution, a distribution of pattern similarity trends that is generated without any human influence at all. And we do that using these world without us simulations. We have many thousands of years with them. Again, these are the same climate models, but now run without any year-to-year changes in greenhouse gases. They just give you the intrinsic variability of the climate system. And I'm stepping through these simulations 300 years at a time, just to give you some flavor of what they look at, what they look like. Again, these are slices through the atmosphere from the South Pole to the North Pole, and from the surface right up to 50 kilometers. And the first thing to note is these things are noisy. They're smaller in scale. They don't show warming of the entire troposphere, cooling of the entire stratosphere. Look at all this little stuff. This is characteristic of natural internal variability. It doesn't give you these kind of global scale simultaneous patterns of warming low down and cooling up high. So we've stepped through 3,600 years of samples here. And again, we're going to compare these patterns of natural climate variability with the model predicted human influence fingerprint, which obviously looks very different from every one of these. And again, we're going to generate some measure of pattern similarity. I'm only showing you the first 400 years of this pattern similarity statistic. The kicker is that the y-axis is the same as in the previous slide that I showed you for the satellite data. So what you can see here is that there isn't much similarity between natural variability patterns and this human influence pattern. So this is just putting them together. Again, this is the pattern similarity between the human influence fingerprint and actual satellite data, showing this big trend. And here on the same scale is the similarity between the human influence fingerprint and these World Without Us runs. And the red lines here are trends over 37-year periods, 37 years being the length of the actual satellite data that we have, 1986 through to 2022. So you can take all of those World Without Us simulations and put them together and get this distribution here in orange, which gives you the pattern similarity that you might expect just due to natural causes. And it has some desirable properties. It's centered on zero. It is symmetrical about zero. So by chance, natural fluctuations in the vertical structure of temperature can give you some time increasing similarity with a fingerprint or some time increasing dissimilarity with a fingerprint. But when we put what we actually got, the pattern similarity trend between the fingerprint and the actual satellite data, that's where we are. We're way, way removed from anything that natural causes alone can do. Which is why, as we said in the paper, it's virtually impossible that any kind of natural variability could give us this observed result here. Why? Why is that? You know, the bottom line is, again, the human influence fingerprint is large scale. It shows, as predicted by Manabe and Weatherald in '67, warming low down, cooling of the stratosphere. That cooling amplifies, it becomes larger the higher you get above the Earth's surface. Natural variability doesn't do that. These are, from these 9 climate models, the typical modes of variability without any human influence, just intrinsic variability alone. And they show anti-correlations between the tropics and high latitudes, for example. They show features that we know and we understand if we study natural variability in the climate system. But they don't look like this, and the satellite data look like this. The satellite inferred changes look like this. They don't look like natural variability. So that basically is why we get the result that we did. Just a few brief conclusions here. We've known since the 1960s that this is a fingerprint of human effects on climate. Burn fossil fuels, increase levels of heat trapping, greenhouse gases. The troposphere should warm, the stratosphere, lower stratosphere should cool. This fingerprinting work that has been done previously, however, neglected this layer from about 25 to 50 kilometers above the Earth's surface, the mid to upper stratosphere. And it turns out that when you include this layer in the fingerprinting, you get a lot of bang for your buck in terms of being able to discriminate between human influence and natural variability. Actually, you get a factor of 5 increase in your ability to separate human and natural effects on climate. Why? It's because this layer, 25 to 50 kilometers above the surface, samples this very large Manabe predicted cooling signal. And it's a region of the atmosphere that has low natural climate variability. And also, as I showed you in the previous slide, it's a region where patterns of natural climate variability don't look like the fingerprint at all. So a lot of things help you if you're trying to identify human effects on climate in the mid to upper stratosphere. As you could see from that comparison of what natural causes can do versus what we actually get in fingerprinting, it is, I think I would now remove virtually, it is impossible to come up with any natural explanation for the vertical structure of atmospheric temperature change. The bottom line is, in the 30 years I've been doing this work, this is the most convincing evidence that I have seen of a human fingerprint on climate. The sun, volcanoes, internal climate variability, either individually or in combination, they just cannot produce this. We produce this. So when folks in Congress, as they still sometimes do, argue, yes, I believe the lower atmosphere has warmed, but it's all natural, that's just untenable. It has been for a long time, but I would argue with this new work, it becomes impossible to explain this vertical structure by any natural causes alone. Only a strong human influence can explain it. And we ignore these fingerprints at our peril. So I think I'll stop there, and I'm happy to answer any questions that you might have about this 30-year odyssey in fingerprinting.
Awesome. Thanks, Ben. That was really interesting and really well explained. I'll add that when I talk about fingerprints of what's causing global warming, and there's a bunch of different potential fingerprints, the one that I focus on is always the cooling of the upper atmosphere, because it's a pretty easy one to explain, and that's also it's a good way to distinguish between solar warming, which, as you know, solar warming would warm all layers of the atmosphere, and human-caused warming, which would cool the upper atmosphere. So I think it's pretty easy one for people to understand, which is really useful.
Right. And, as you could see from the time series stuff back at the beginning, the solar signal in the stratosphere is small. Yeah, this one. Here's the solar signal, this roughly 11-year cycle, and relative to the overall cooling, it's trivially small. So solar just can't explain what we've actually observed and monitored.
Yeah. So while you're on that slide, something I probably just missed it, but are the stratospheric temperatures, did we already have those, or is this relatively new data, or what's the story there?
Oh, great question. So we did have the stratospheric data for these three channels. We had them from two groups. One Chengxi Shu's group at the University of Maryland, a NOAA group, and the other John Nash and colleagues at the Hadley Center in the UK. Unfortunately, those two groups yielded very different results for what was happening here. And David Thompson and colleagues published a paper in Nature in 2012 entitled "The Mystery of Stratospheric Trends," where they presented the field with this puzzle. Hey, these are two groups. They're analyzing the same data. They get quite different results. Nothing new there. That was the history here on this side of things, with different groups looking, particularly in the troposphere, at the same raw bits and bytes, but arriving at very different estimates of the magnitude of tropospheric warming. So it was considered that these data sets here, because of this difference between the two groups, weren't mature enough for fingerprinting. And through a lot of hard work involving the two groups and other scientists, they really resolved the differences between the Hadley Center estimates and the estimates of the NOAA group. Now, why haven't we used the Hadley Center estimates here? It's because they don't provide patterns. Only the NOAA group provides patterns, which, as I mentioned, are an essential component of the fingerprinting. But it took a while until these two groups at the global mean level came up with more similar results. And that's why I think nobody has done fingerprinting in this region of the atmosphere until our study. Our study really was the first to try and do pattern-based fingerprinting in this layer of the atmosphere. Does that make sense?
Yeah, cool. That makes sense. That's really interesting. Okay, so let's go to some audience questions. We'll take one from our YouTube watchers first. Somebody asked in one of your earlier slides, it showed that water vapor is the most abundant greenhouse gas. And so basically the question is like, can we do something about water vapor?
That's a great question. And we have done something about water vapor. So we also have satellite measurements of the total water vapor in Earth's atmosphere, something called total column water vapor. And these are from these beautiful satellite measurements that look directly at the microwave emissions from hydrogen. And those emissions are proportional to the amount of water vapor in the total atmospheric column. So we used those satellite measurements back in 2007 and 2009 to show that the observed increase in water vapor and the pattern of increase, so the moistening of Earth's atmosphere, was a fingerprint of human effects on climate. So let me back up. When we burn fossil fuels, increase atmospheric CO2, a warmer atmosphere can hold more moisture. That's been well known for a long time. There's something called the Clausius-Clapeyron relationship, which governs that relationship between temperature and something called saturation water vapor pressure. And it turns out that the pattern of water vapor change, which basically shows water vapor increases everywhere, is very different from natural variability patterns in water vapor. If you look at natural variability of water vapor patterns, they look like El Niños and La Niñas. There are places where water vapor increases during an El Niño, places where it decreases. You don't see water vapor increasing everywhere, with the largest increases over the warmest areas of the tropics. So, the kicker is that we are changing water vapor. We have changed water vapor by burning fossil fuels and increasing increasing temperature. We've moistened the atmosphere, and that pattern of atmospheric moistening has real discriminatory power. Just like everything I presented today, it enables us to say the pattern of moistening that we see in the atmosphere as measured from space with satellites is not natural. And it's, as I was mentioning a little earlier today, it's really relevant to these current discussions about the moistening of the atmosphere and severe flooding and storms. And what do we know about that? Well, we know very well that by burning fossil fuels and increasing CO2, water vapor is responding to that. And that response amplifies the warming that we're causing by increasing CO2. I guess that's the best way of putting it.
Yeah, basically water vapor is a feedback. And so if you want to reduce water vapor and the warming it causes, then first reduce CO2 and reduce temperatures, and water vapor will follow.
Exactly.
Cool. So then we got a question from Lori on your slide 25. So she asks, I understand your point that the observed pattern looks different from the natural variability patterns. But it looks like there's some very dark red and dark blue natural variations possible. Am I seeing that correctly? Are those dark areas larger temperature changes than we are actually observing?
Yeah, great question. And there's something called the Brewer-Dobson circulation, which is influential in the mid to upper stratosphere. And what we see here in these natural variability patterns, as I mentioned previously, is some evidence of that type of variability. This anti-correlation or out-of-phase relationship between temperature changes in the tropics and at high latitudes. Same here, except this is a difference between the two poles. So yes, natural climate variability can generate these wiggles, which you could see in the time series slide, even in the mid to upper stratosphere. The kicker is it can't do this. So when we when we look at the satellite data, we over 37 years, we see this, we don't see this. And I think that's the salient point here, that the long-term observed changes in temperature show this curious simultaneous warming of the lower atmosphere sustained from the South Pole to the North Pole, and cooling of the upper atmosphere, again, sustained across all latitudes. And natural climate variability doesn't do that. Let's go back to this figure here, which illustrates that nicely. Okay, so these are just the trends over this 37-year period, 86 to 2022, in the individual climate models. This MMA is the multi-model average of these 9 models. All of them, although they show differences, show this coherent warming of the troposphere and cooling of the stratosphere. And that's what we see in these 2 different sets of observations as well, where the differences in the observations are in these 3 lower layers, the lower troposphere, the mid-troposphere, and the lower stratosphere. But this does not look like natural variability, which is essentially why we get the fingerprint result that I showed you later. This is why we get this. Natural variability looks like this, and the satellite data look like this, and we are worlds apart. Natural causes can't generate the kind of pattern similarity that you just saw in that previous slide between the actual satellite data and the model human influence simulations.
Cool. And back on slide 25, were the scales the same? So like the dark reds, were they the same? I guess they were, huh?
Yeah.
Natural variability. Okay.
Yeah.
Okay. Cool. So then Rachel says this is the first that she has heard of fingerprinting, and she asks if you can explain the process and what it means to do fingerprinting a little bit.
Great question. And let's get back to this figure here. So the premise in fingerprinting is that patterns have value. Patterns of different influences on climate are different. And you can see that visually without getting into the details here. Again, these are purely model simulations, slices through the atmosphere from the North Pole to the South Pole, from the surface up to 30 kilometers. And the beauty of model world is you can do these thought experiments that Einstein was fond of, Gedankenexperimente. You can change just one thing at a time. The sun, human-caused greenhouse gas changes, particulate pollution, human-caused ozone depletion, natural changes in volcanoes. According to our best understanding of how those things have actually changed, say over the 20th century, you run a climate model with that, and you can see that these patterns are fundamentally different. As Dana, as you pointed out, if indeed there has been some small uptick in the sun's energy output over the 20th century, you would expect to see heating throughout the full vertical extent of the atmosphere. But that's not what we see in the satellite data, as I showed you. So this sun explains everything, which people have invoked as the cause of all global warming at the surface. Well, that's what it would look like. If that hypothesis were correct, and the sun was the sole cause of the observed global surface warming of roughly 1.2 degrees Celsius from 1880 through to the present, then that's what we should have seen in the upper atmosphere. But that's not what we saw. What we saw is this. So that's the power of fingerprinting, that by looking at patterns, it enables us to convincingly try and address certain hypotheses, like, this, I believe the sun explains everything, or I believe natural causes, internal cycles in the climate system explain all observed climate change. We can look at those hypotheses and rigorously test them, which is what we've done here. And they fail. The only explanation of this observed behavior, again, observed behavior that was predicted over 55 years ago by Manabe and Weatherald, is human-caused increases in heat-trapping greenhouse gases.
Great. So we got a couple of similar questions from Mark and Travis about solutions in psychology a little bit. So does your research give us any potential interventional options for solving the problem? And to solve the problem, we have to change people's minds. So is there some way we can use your research to change people's minds about the problem and solutions?
Wow. Let me take the second part first. Can we change people's minds? I don't know. Part of the motivation for doing this work was to diminish the wiggle room for climate change deniers. So again, there are folks who would argue that all global warming is natural: sun, internal cycles, volcanoes, some combination thereof. We have looked at those hypotheses rigorously, time and time again. They cannot explain this or this, the actual observed changes. Only human influence, which is what all these model simulations were run with, can explain the observations. And this result is now so clear and so unambiguous. Again, this difference here is stunning. Look at this. You're, I think, somewhere in the vicinity of 40 standard deviations. The observed result is 40 standard deviations removed from the mean of this natural variability distribution. If you tried to convert this distance into a number, you're in astronomical territory. The odds of getting this by natural causes are virtually impossible. And I think it's important to restate these things, to say, okay, we're going to look at a long-standing projection and see whether they were right. And they were. Manabe and Weatherall, 1967. We're going to do the math, do the fingerprinting, and compare patterns. Not just what Manabe and Weatherall did, look at global mean changes, but see whether any kind of natural patterns might be able to explain what we've measured and monitored. They can't. You could see with your own eyes the power of fingerprinting, that the human influence pattern is fundamentally different from the smaller scale, noisier patterns of natural climate variability. To me, to get at the second part of your question, it seems critically important to keep on hammering home the science, to keep on confronting those who would argue that it's natural or that it's not happening, to get this evidence in front of them as often and as forcefully as one possibly can. That's my life's work. That's what I'm going to continue to do. That's what you and many others have done, Dana. It's critically important to continue talking about evidence and to continue telling people, be great if all this were natural. It isn't. Sorry. And that leads to what can we do about it? And I think the first part of your question was intervention strategies. And I'm not sure whether you meant that in terms of geoengineering. Perhaps you could clarify. What did you mean in terms of intervention strategies?
That's a good question. I'm not sure what was specifically intended by the intervention word there. Interventional options. But I guess they're asking, is there anything specific to your research that tells us what we should do in terms of solutions?
Well, my very good friend and dear friend, Peter Joseph, would say, put a price on carbon. We're not going to solve the problem in the absence of a rational price on carbon. And I agree with him. I think that the science alone, no matter how compelling it is, has not shifted the needle, fundamentally shifted the needle in terms of addressing the problem of reducing emissions with the urgency that we need. So to Peter, to thousands of renowned economists around the world, and increasingly to me, it seems evident that we need to put a price on carbon. And I think that's likely to be the most effective solution we have, the most powerful tool in the toolkit.
I think everybody in the room here is going to agree with you on that. You're preaching to the choir here. How long, going back to the water vapor question, how long does it take water vapor to equilibrate with changes in CO2?
Ooh, that's a very good question. And I think the answer to that sort of depends on where you are in the atmosphere, whether you're in the troposphere or you're in the stratosphere. And there are people who look at water vapor transport and try and get at those timescales using atmospheric tracers. I'm not really knowledgeable about that work. That said, if I were to show you a figure in the tropics, which I have, but probably can't find quickly enough for us,
sure,
the figure would show time series in the tropics, 20 north to 20 south, so averaged over 20 north to 20 south. And it would have two panels. One panel would be the satellite inferred change in lower tropospheric temperature. And the other panel would be the satellite inferred change in water vapor over oceans. And they are in virtual lockstep. So every little wiggle in the satellite temperature data for the troposphere is reflected in the water vapor in the troposphere. This is primarily a measure of water vapor that is weighted to where most of the mass of the atmosphere is, which is in the troposphere. So the bottom line is that in the tropics, at least on timescales of weeks to months, water vapor is very, very tightly coupled to the temperature changes. If you get higher up in the atmosphere and if you get into the Arctics, then things are a little bit more complicated. But at least in the tropics, which, you know, most of the globe, area of the globe is in the tropics, there's a very tight coupling between the troposphere temperature changes and the water vapor changes.
And with that, we have reached the very top of the hour. So we are so grateful for all of us that have tuned in live and the many, many hundreds more that will be joining for the recording. If you are curious about where you can find the recording to share with those that couldn't make us live, I've put the link to it in the chat. It's simply cclusa.org/YouTube. And we do invite you after tonight to continue to join the lively discussion that many of you here tonight live are a part of with our Nerd Corner. That's simply cclusa.org/nerd-corner. Dana and the team are doing a wonderful job of continuing to engage on all things climate science, tech, policy, and economics related. So With that, I'm going to unmute all lines so that we can join in a raucous round of applause for your time and availability tonight, Dr. Santer. Thank you so much for joining us, and know that you always have a fan club here in CCL. We can't wait to have you back and all ahead, and just keep up the amazing work that you're doing. So with that, I'm going to unmute all lines.
Well, thank you very much, Brett and Dana, for giving me this opportunity, and thanks for the good you do in the world, trying to advocate for effective solutions to this problem. My job is relatively easy. Your job is the critically important one.
I think we need each other. Thank you so much, Ben. Stay safe, everyone. Have a wonderful night.
Thank you for listening to this episode of Citizens Climate Lobby's training program. You can tune into more episodes anywhere podcasts are available. Inspired by what you heard today? Join Citizens Climate Lobby to advocate for bipartisan climate solutions. Go to community.citizensclimate.org to find more trainings, resources, your local chapter, national action teams, discussion forums, and more. Be sure to like our Facebook page and follow us on Twitter and Instagram @CitizensClimate. We also invite all of our listeners to subscribe to our YouTube channel for more inspiration.
Like what you hear? Recommend us to your friends and make sure to give us a 5-star rating. It helps us show up on other listeners' feeds. Feel free to pass on any suggestions for future episodes in the comments as well.
And together, we are creating the political will for a livable world.